All right, thank you, Stephanie. So welcome everyone. I'm here to talk to you today about something that I didn't really think was possible at first, but it's going to be interesting. So the idea of backdoors is kind of thrown around a lot today to the point that it's largely lost all meaning. But what I'm going to talk to you about today is not the management engine, it's not the platform security processor, it's none of the things that people are normally so concerned about. It's something that we never really saw coming, and I think something a lot more interesting. But before I begin, like any good research, I start off with a disclaimer. I did all of this research on my own, in my own time, while I was an independent consultant, and none of this reflects in any way the beliefs or actions of my current employer. But with that, my name is Christopher Domas. I'm a cybersecurity researcher. I've tinkered with a lot of different things over the years, but for the last couple of years, what I've been interested in is low-level processor exploitation and vulnerability research. So let's start off with a demo of kind of what I mean by that and the kinds of things we can unlock. And specifically, let's look at what we're going to explore today in this presentation. So I am logged into a system, just a regular system, unmodified, running default OS configuration. I'm logged in as an unprivileged user named Delta. I'm going to open up a .c file called demo.c. And demo.c is a very simple file. All we do is we load an address into the EAX register, then we've got a label, and then we've got all of these bound instructions. So the x86 bound instruction is not a very common instruction. You might not be familiar with bound, but the idea behind the x86 bound instruction is it will take an address and it will take a second address and see if the first address is within the bound specified by the second address. Now you'll notice this bound instruction has a rather unusual set of second addresses associated with it. These are basically look like random numbers. And in fact, this processor does not have access to the memory at that address that's being specified. And like anything else in x86, if you don't have access to the memory that you're trying to use, you will get a general protection exception, or in Linux, a segmentation fault. So despite the fact that, despite the fact that all of these registers we know are going to cause segmentation faults at the end, we're still going to try to launch a shell and see if anything happens. So let's give this a try. We'll compile this little program. We will execute it, and sure enough, just like we expected, we get a segmentation fault, and our user hasn't changed. So that's nothing terribly interesting here. But if I go back into this program, and I'm going to make one tiny little change. I'm going to add one x86 instruction. It's an instruction that's so secure or so obscure and unknown, it doesn't actually have a name. In fact, it's not supposed to exist. I have to write this in machine code. OF3F is the one instruction I'm going to add to the beginning of my executable. And when I execute this instruction, the fundamental nature of all the subsequent bound instructions is going to change. And what I'm going to be able to do is use those instructions to reach directly into the kernel, bypassing all of the processor's security mechanisms in order to give myself root access on this system. So this kind of thing is not supposed to exist. And the rest of this presentation is going to be a long, convoluted journey, sort of seeing how I came across this feature. And the whole thing begins with the idea of rings of privilege. So in the beginning, 30 years ago in x86, there was no concept of separation of privileges on the processor. Basically, any code running on the processor had the same permissions as any other code running on the processor, and things were basically chaos. There was nothing stopping Minesweeper from having the exact same privileges as the kernel, and that's not a good situation to begin. And so 30 years ago, they implemented the idea of separation of privileges, different rings of execution on x86 processors. And the idea was something like this. Only some code would have complete unfettered access to the entire system, unrestricted access to the system's hardware. And that was the kernel code that would live inside of the most privileged ring, ring 0. Then outside of ring 0, slightly less privileged code would live in ring 1, less privileged than that in ring 2, and our least privileged code, where we would throw all of our user code, would live in ring 3. And that fundamental idea of separation is why we can have some sort of confidence that our Minesweeper game is not also harvesting credentials from my banking account sitting in another process, because in order for ring 3 code to do anything of importance, it has to go through very, very strict, careful hardware security checks in order to ask ring 0 to do something for it. So that's the fundamental basis of all security in x86 processors today. But we started digging deeper. basically, this ring model wasn't well suited for running multiple operating systems on one processor. We needed something more privileged than ring 0 in order to handle that. So we invented the hypervisor. And since it was more privileged than ring 0, colloquially, we kind of called that ring -1. But there's some things we didn't want the hypervisor to do. We threw all those things into system management mode. And since that was more privileged than the hypervisor, we called that ring -2. And then a couple of years ago, some researchers came along and they said, hey, there's this entirely different processor sitting on the platform that can actually do things that the x86 processor can't do. So we started calling that ring -3. And it's just sort of getting ridiculous at this point. But if you've been following this research as it's sort of expanded over the last 20 years, in the back of your head, you've probably been thinking, like, can we go further? How deep does this rabbit hole go? And that's sort of the question I set out to answer when I went down this path. So when I'm sort of beginning research on something really big and unknown, I found a good place to start is sometimes with patents, because sometimes you can find information in patents that you can't find in any other documentation. So given this idea of this privilege model, of these rings of privilege on x86, imagine my surprise when I was sifting through patents and I saw this little blurb just sort of nonchalantly buried in the middle of a patent on a completely different idea. It said, additionally, accessing some of the internal control registers can enable the user to bypass security mechanisms, for example, allowing ring 0 access at ring 3. My head kind of exploded when I saw this. Like, all of our security on x86 is based around this idea of rings of privilege. And this little blurb is telling me there may be some way to circumvent all of that in one fell swoop. But they go on to say, in addition, these control registers may reveal information that the processor designers wish to keep proprietary. Well, that's kind of understandable. If I had some circumvention for all the privilege mechanisms on the processor, I'd probably want to keep that proprietary too. But then they go on to say, for these reasons, the various x86 processor manufacturers have not publicly documented any description of the address or function of some of the control MSRs. So that makes sense, but that means we're probably dealing with something undocumented that we don't have a lot of access to. So I did what any rational person would do in this situation. I went out and bought 57 computers to start doing some research on to see if I could dig into this idea a little bit further. So I had some idea, based on the patent owner and the patent time frame, I had some idea for what processor I might be trying to look at here. But patents are a funny thing where the intellectual property gets bought by different entities and ideas sort of trickle through the industry in weird ways. So I sort of wanted to cast a wide net to try to analyze this idea of a ring circumvention mechanism. But eventually what I settled on was a processor with, or a system with a VIA C3 processor. So VIA is one of the 3 major x86 manufacturers, and C3 is a model that they had a while back. So these were specifically targeted at embedded systems. They're marketed towards point of sales, kiosks, ATMs, gaming. Since we're in Vegas, you might want to start poking around after this. Digital signage, healthcare, digital media, industrial automation, and of course, you can still find them in PCs and laptops. So this was the system I eventually pulled off my shelf for this research and what I'm going to talk about for the rest of this presentation. This is a thin client with a C3 Nehemiah core inside of it. And I'll talk later on about how this issue might affect other processors, but for now, that's the system we're going to be focused on. Now, I was unable to find a developer manual for this processor. That would have been a really useful starting point, but even the patent sort of hinted at the idea that a lot of this stuff's not going to be documented. So that means we have to find some other path forward. So what you can do in the situation, what I did was sort of try to follow a trail of patent breadcrumbs, just try to read different patents that might be related to one another in order to try to piece together as much information about this backdoor as I can. So this quote isn't actually from one of the patents I ended up using. This was just another patent that I stumbled across along the way. But in order to give you some idea of what kind of things you're dealing with when you're reading this patent literature, I want to quickly give you an example of some patent speak. So this says figure 3 shows an embodiment of a cache memory. Referring to figure 3, in one embodiment, cache memory 320 is a multi-way cache memory. In another embodiment, cache memory 320 comprises multiple physical sections. In one embodiment, cache memory 320 is logically divided into multiple sections. In one embodiment, cache memory 320 includes 4 cacheways, i.e. cacheway 310, cacheway 311, cacheway 312, and cacheway 314. In one embodiment, a processor sequesters one or more cacheways to store or to execute processor microcode. This is the most convoluted legalese I've ever had to sift through, and it is just so incredibly tedious trying to derive any information from patent literature. So you can imagine how awful it is to try to sift through 100 pages of of this kind of text. And just to put that in perspective, that one 4-page patent had the phrase "in one embodiment" 142 times. Like, trying to do research this way is absolutely painful, but if you're persistent, it can start to pay off. So after a lot of work, I narrowed in on these 6 patents that seem to have some loosely related ideas that might be able to point me in the right direction for circumventing the ring privilege model in x86. So some of the key ideas from these patents that I sort of narrowed in on was it looked like at the time VIA was embedding a non-x86 core alongside their x86 cores in the C3 processor. This non-x86 core was a RISC-type architecture. And the patents didn't have a consistent term for this, but I started calling this the deeply embedded core, the DEC. They also talked about something called a global configuration register. It was a register that would be exposed to the x86 core through a model-specific register. And the patent suggested that this global configuration register could activate the RISC core. They also talked about what was called a launch instruction. It would be a new instruction added to the x86 instruction set architecture, where once the RISC core was activated, you could use the launch instruction to start a sequence of RISC instructions. So where does that leave us? Well, this is all sort of wild speculation at this point, just piecing together little pieces of different patents. But if our assumptions about this deeply embedded core are correct, that means it could be used as sort of a backdoor, a means of surreptitiously circumventing all of the processor security checks. So that's obviously something worth diving into a lot further. So let's start at the beginning. How would we go about activating this circumvention mechanism? Well, there's 3 little tidbits from the various patents I was able to pick up on that might point us in the right direction here. We've got one patent that says a model-specific register can be used to circumvent processor security checks. We've got another patent that says a model-specific register can be used to activate a new instruction in x86. And we've got a third patent that suggests that a launch instruction can be used to switch to a RISC instruction sequence. So if you put these 3 things together and sort of fill in the gaps, it sounds like there's some model-specific register bit that enables a new x86 instruction that activates a RISC core that can bypass the processor security checks. So let's start with the first step in that chain, this model-specific register. So just a little bit of background for people not familiar with the idea of MSRs on x86. So MSRs are 64-bit control registers, and they're really, really varied. They're used for things like debugging and performance monitoring and cache configuration and feature configuration. Basically, anything not directly related to computation can be tossed into the MSRs on x86. And unlike the registers you might be more familiar with, like EAX or EDX on x86, MSRs are accessed by address, not by name. And the MSR addresses go from 0 to 4 billion. So the way you access a specific MSR is you load its address into the ECX register, and then you use the read MSR and write MSR instructions in order to access the contents of that MSR. So theoretically, one of these MSRs will allow us to eventually bypass security mechanisms on the processor, but there's a saving grace here. You can only access MSRs from ring 0 code. So even though we might be able to enable a backdoor on the processor, it should require one-time ring 0 kernel level access in order to activate, or maybe not. We'll revisit this part later, but just so that we can move the research forward for now, let's assume that we have one-time ring 0 access just to tinker with the MSRs in order to get the rest of this chain active, and we'll revisit that limitation later on. So going back to that original patent I talked about, they do mention that the various x86 processor manufacturers have not publicly documented any description of the address or function of some of the control MSRs. So that leaves us in a bit of a conundrum. If we don't have any documentation for which MSR we're looking at, how are we going to find the one that activates these secretive features? So step 1, it seems, would be let's just figure out which MSRs are implemented by the processor. Ignoring any documentation or anything else like that, let's figure out which MSRs actually exist on the processor. And this one's a pretty easy one to solve. Basically what you can do is in a kernel module, set your general protection exception handler to be a specific function under your control. You can do that with the LIDT instruction to reconfigure that exception handler. Then you're going to load an MSR address into the ECX register. So let's say I wanted to figure out, does MSR 1337 exist on this processor? I'll load 1337 into the ECX register. Then I'm going to try to read that model-specific register. And then if I don't get a fault, that means that the MSR exists. Whether or not the documentation says that MSR exists, it must exist if I don't get a fault. On the other hand, if my exception handler gets control, that means that MSR does not exist. So this is a really, really simple way to iterate through all the possible MSRs and figure out which exist on the processor, which don't exist on the processor. So when I ran this little algorithm on my target C3 processor, what I found were that it had 1,300 implemented model-specific registers, and that is way more than would be typical on an x86 processor, and kind of threw a wrench in this whole process. That's too many MSRs to analyze. I think one bit in one of these MSRs is going to activate this new x86 instruction, but I can't sift through 1,300 MSRs on my own. So the next question is, well, which of these MSRs are actually unique? Which really could be the ones that I'm looking for? What are the interesting ones that I should be focused on? So I came up with this idea for sort of a timing side channel attack on the processor, where basically what I would do would be to calculate the access times for all 4 billion possible MSRs. So what that looks like is we have a read MSR instruction, and then on either side of that read MSR instruction, we have some serialized read timestamp counter instructions. And that lets me measure exactly how much time it takes to read any given model-specific register. So what that ends up looking like is this. On the x-axis here, I've got my 4 billion possible MSRs on this platform. On the y-axis is the amount of time it takes to access each of those MSRs. In green, I'm showing the MSRs that actually exist on the processor. In red are the unimplemented MSRs. So this gives some really, really interesting insights into the processor that would normally be totally off limits to us. We can actually sort of peer into the microcode and understand what's happening with these various MSRs using this timing side channel. So I want to throw out an observation here, namely that functionally different MSRs should have different access times. So for example, accessing the timestamp counter MSR should take a different amount of time than accessing a thermal sensor MSR. And that's because each of those MSRs is going to have different microcode implementing them. That microcode is going to take different amounts of times to execute. So I would expect the access times for each MSR to be different if the MSRs are very different. On the other hand, functionally equivalent MSRs should have approximately the same access time. So for example, there's something called the MTRR, the memory type range registers in x86. It's a set of MSRs that control cache behavior for different regions of memory. What I would expect would be that MTRR 0 would have roughly the same access time as MTRR 1, because even though they control different regions of memory, they're functionally equivalent MSRs. So what that means is that this timing attack gives me a way to differentiate between like and unlike MSRs. And I'm going to define like MSRs as adjacent MSRs with equal or functionally related access times. So then specifically, I'm going to throw out this hypothesis that the global configuration register, this model-specific register hinted at in these patents, is probably unique. It doesn't make sense to have multiple functionally equivalent versions of the GCR. This thing should have a bit that activates a new x86 instruction that I can use for circumventing protections. And it doesn't make a lot of sense to have several of these different registers all doing the same thing. So when I start looking at my timing graph, I can begin to pick out the functionally unique MSRs in this graph. It's the ones that are separate from the other MSRs on the system. So when I begin to identify the functionally unique MSRs, I'm able to actually pare down that original list of MSRs a lot more. So using this side channel, I found 43 unique model-specific registers from the 1,300 that are actually implemented on the processor. So that's really exciting for me. That means it seems like my research can move forward. 43 sounds like a much more tractable number of model-specific registers to analyze than 1,300. The problem is 43 MSRs is still 2752 bits to check at 64 bits a piece. That is a lot of bits to sift through. I want to find one bit that activates this launch instruction, this new x86 instruction, but that's too many bits for me to go through by hand, especially when you consider the magnitude of the x86 instruction set. So theoretically, one of these bits enables a new x86 instruction. Well, if we look at how many possible x86 instructions there can be, it turns out there's a lot. x86 is a really, really complicated architecture, and an upper bound on the number of possible x86 instructions would be something like 1.3 undecillion instructions. So I'm looking for a single new instruction amongst 1.3 undecillion possible instructions. Even if I take a really, really generous estimate and say that I can scan 1 billion possible instructions a second, we can do like a quick Fermi calculation to see like 1.3 undecillion divided by a billion, divided by 60 seconds in a minute, divided by 60 minutes an hour, divided by 24 hours a day, divided by 365 days a year, means scanning for a new instruction in x86 is going to take approximately 1 eternity. So I don't have time to sit around waiting to find this new instruction, especially when I've got to do a scan for every bit. Then I'm looking at about 2,700 eternities trying to find which bit activates this new x86 instruction. So I was really fortunate in this case because I actually looked at this exact problem last year and developed this tool called SandSifter. So what SandSifter does is it finds an intelligent way to scan through the x86 instruction set. It uses page fault analysis and a depth-first search algorithm to quickly find all the x86 instructions of interest on a processor. So I still can't run SandSifter 2,700 different times. It takes about a day to scan a processor, but this at least opens up some opportunity for moving forward. What I can do is I can look at each of those 2,700 candidate MSR bits, and I can try to toggle each of them one by one, not doing an instruction scan between each one, but I can just try to toggle each of these bits one at a time. Of course, I'm going to run into some problems. These are configuration bits that control the deepest workings of the processor, and I have no idea what they do. So a lot of them are going to lock the processor, freeze the OS, panic the kernel, or just reset the system entirely. So this is still something that's not really doable by hand, but we can automate this process. So I developed a simple setup where I would have a target system, the VSC3 processor, would have a wire soldered onto its power switch, and that wire is connected to a relay, and that relay is connected to a master system. The target system boots from the master over the network, and the master system can SSH into the target and assign it jobs. Basically, it can SSH into the target and start toggling its potential MSR bits one by one. And what the master will do is it will detect when the target is frozen or panicked or locked and use that relay in order to power cycle the target. So this way I can automate the process of trying to toggle each of these 2,700 MSR bits one by one in order to see how many can I get on before the system becomes unstable. So through hundreds of automated reboots, this thing ran for about a week, and I was able to identify exactly which of those bits could be toggled without the system having any sort of visible side effects. So with that done, I would go in and I would toggle all of the stable MSR bits that I could possibly access, and then run the SandSifter scanning tool in order to see if any new instructions had appeared on that x86 processor. So that looks something like this. So SandSifter is scanning the system for new instructions using its page fault analysis depth first search thing. I sort of started watching this, taking this video in the middle of a search, but if you let this scan for about a day, what you'll eventually find is SandSifter will spit out some new information for us. So there we go. After about a day of scanning, SandSifter finds exactly one new instruction in x86 that was not supposed to be there. It finds OF3F. So judging from the patent literature, this is what they're calling the launch instruction. This is the new x86 instruction enabled by some bit in the global configuration register. So with GDB and a little trial and error, I was able to figure out that this launch instruction is effectively a jump EAX instruction. It just jumps to whatever address is in the EAX register. So now I want to know which of those bits that I activated was really responsible for enabling this launch instruction. Fortunately, now that I know what the instruction is, I no longer have to run complete SandSifter scans in order to test my theories. Basically, what I can do is I can activate a candidate MSR bit and see if OF3F exists on the processor. If it doesn't, that wasn't the correct MSR bit. If it does, then I found the bit that I'm after. So using this approach, I was able to determine pretty quickly that MSR number 1107 on the processor activates this launch instruction. So 1107 must be what the patents are calling the global configuration register, the register that will unlock this new functionality. Going further, what I suspect at this point is that by unlocking this other RISC core on the processor, I will be able to use that core to circumvent all of the security checks built into x86. That really opens up some phenomenal opportunities in exploitation. So because of that power, I called that specific bit in MSR 1107, the God mode bit, is basically bit 0 of that register was the one ultimately responsible for enabling this new x86 instruction. So with this, I've figured out the God mode bit. I figured out what the launch instruction is. Now the question is, how do I actually execute instructions on this RISC core? So we can dive into the patents a little bit more to try to speculate on how this might work. And the patents include some interesting figures for this dual instruction set pipeline. And what they suggest is that sometime after fetching an instruction, that instruction might be sent to the x86 core, or if the RISC core has been activated, it might be sent to the RISC core. So I went through a lot of trial and error and a lot of different models for exactly how this would work. And I ended up settling on something like this, where what's essentially going to happen is an instruction is going to be fetched from the instruction cache, and it's going to go to some x86 pre-decoder that's basically going to break that instruction apart into its basic components. Then those components are going to pass a check. The processor is going to check, has the RISC core been activated with that launch instruction or not? If it is not, it's going to pass those components over to the full x86 decoder, and those are going to go through the x86 pipeline. If it has, it's going to break off one of these components and send it over to the RISC decoder and execute that as a RISC instruction instead. In other words, with this setup, there's some x86 instruction where if the processor is in RISC mode, it can pass a portion of itself over to the RISC processor. And since this x86 instruction essentially joins the two cores, it joins the x86 and the RISC core, I started calling this the bridge instruction, but we don't know what this instruction is yet. So I have no idea how to actually feed instructions to this RISC core that I've activated. So to find the bridge instruction, it should be sufficient to detect that a RISC instruction has been executed, but that's easier said than done. I have no idea what this RISC core looks like. I don't know what instruction execution on that core should look like. So how are we going to detect if we've successfully executed a RISC instruction? Well, there is one easy way. The theory here is that if this core actually does provide a way to get around the processor security checks, then there should be some RISC instruction that when executed in ring 3 would corrupt the system. Basically, that would give us something really easy to detect. If the processor locks or the kernel panics or the system resets, that would be a sure sign that we executed a RISC instruction, because none of those things should be able to happen if you're just executing ring 3 x86 instructions. So if we detect any of that behavior, we know that we've found a corrupting RISC instruction and therefore found the x86 bridge instruction as well. So to explore this, I sort of tore apart the heart of SandSifter and repurposed it for brute force fuzzing of the processor. And what SandSifter is going to do now is it's going to execute that launch instruction before every x86 instruction that it generates. And what SandSifter is trying to do is it's trying to generate a processor lock. And you'll see that we just did that after fuzzing the processor for a little bit. And basically, when you observe that the processor is locked, when from ring 3 we locked the processor, that indicates that we've found that bridge instruction that we're looking for. We've found a way to send commands to that x86 core, or to that RISC core embedded alongside the x86 core. So it takes about a full hour of fuzzing to find this, but what SandSifter uncovered was that a bound EAX instruction in x86 is able to send instructions over to the RISC core after that core has been activated. Specifically, bound EAX has a 32-bit constant value in it, and it's this 32-bit constant value that forms the actual RISC instruction that will be sent to that deeply embedded core that might be able to bypass processor security checks. So we're getting further. We figured out how to execute instructions on the deck. I use this bridge instruction to send it in RISC instruction. So the next question is, what do I actually want to execute? Like, what do these instructions look like? What architecture am I even dealing with? If I want to use this to actually circumvent security checks, I need to answer these questions. So the obvious first approach to dealing with this unknown architecture is just assume that it's some common architecture. There's really no need to reinvent the wheel, adding a new core to your x86 processor. So maybe this thing is some common architecture that we've seen before. So to test that, we could basically try generating simple instructions in some common architecture, like ARM, PowerPC, or MIPS. I might generate an instruction like add 1 to R0 for ARM, and I could try executing that on the deeply embedded core and see what happens. The challenge here is, without knowing anything about that deeply embedded core, there's no obvious way for me to necessarily check the results of an instruction. So sure, I can generate some simple RISC instruction and try to execute it, but I don't know what I'm looking for after it executes. So the good thing here is that there is still a simple way to rule out architectures. What I was observing is that a lot of the RISC instructions I tried to execute would actually lock the processor. So if I generated a really simple instruction like add 1 to R0 for a RISC architecture, and I tried to execute that on the DEC, and the processor locked up, that's a pretty good sign that that wasn't the architecture that I was expecting. So I can rule out that this is ARM if it's choking on simple ARM instructions. Unfortunately, when I took this approach, I pretty quickly ruled out 30 very common RISC architectures for that deeply embedded core. Now, I still think that this thing is probably based off of some common architecture. There'd be no reason to spin something up from scratch, but it's probably heavily enough modified that I couldn't recognize it. So that means I've got to sort of deal with this deeply embedded core as a black box. I've got to treat this as an unknown architecture and figure out how to actually communicate with it. So to do that, we've got to basically reverse engineer the instruction format for that deeply embedded core. And I spent enough time on this, I made up my own name for this. I started calling it the deeply embedded instruction set, the DIEs. So let's look at what this DIEs might look like and how we might begin to reverse engineer it. So one idea would be we could execute a RISC instruction and basically try to observe its results. Like I said, the challenge with that, though, is we don't know what the RISC ISA looks like, so there's not necessarily an easy way to observe the results of an instruction. But as I started reading more into the patent literature, I saw that there were hints that this RISC core and the x86 core had a partially shared register file, which means we should be able to observe the results of at least some of these RISC instructions from the x86 core. So this is a diagram from the patent literature where they're sort of showing an ARM core and how some of the registers are shared with the x86 core on the processor. So what that means is we could do something like this, and this is just sort of a rough summary. We could generate a processor state, so we could generate some buffers in kernel memory, generate some buffers in user memory, generate a state for all of the processor registers, and we could load that state onto the processor. After we've loaded up this state, we'll execute the launch instruction, followed by an x86 bridge instruction. The bridge instruction will feed a RISC instruction over to the deeply embedded core and let that instruction execute. After that instruction executes on the deeply embedded core, what we're going to do is read the state off of the processor. We'll read out all the registers, we'll read out all the buffers that we set up, and then we'll see if anything's changed between that input and output state to see if we can start deciphering what effect that randomly generated instruction had. So nothing's ever simple with this. Another challenge came up. I'm dealing with an unknown instruction set with unfettered access to ring 0. So I'm just trying to randomly generate these RISC instructions and see what happens. But it turns out it's really, really easy then to generate an instruction that causes a kernel panic or a processor lock or system reboots. And in practice, I could only execute about 20 random RISC instructions before the system became unrecoverably corrupted and had to be rebooted. So even after optimization, the fastest I could get one of these systems to boot was about 2 minutes. So some quick calculations suggested that gathering enough data to reverse engineer the entire instruction set at this rate was going to take months and months. So I decided to expand the original system that I had built for fuzzing this. So what we see down here are, instead of 1 target, I've now got 7 of these thin client targets. If you look closely, you can see a little green wire coming out of the chassis of each of these, all hooked up to this relay up here. The relay is hooked up to a master system that can use that relay in order to power cycle each individual target. The target's network boot through the master, and the master, once each system is booted, will SSH into the target and give it a fuzzing task. The master records the results of the fuzzing as they occur into a database, and when it detects that one of these targets has become corrupted, if the kernel is panicked, the system's frozen, or what have you, it will use the relays in order to power cycle that specific frozen target. So we can see what this thing looks like in action. So what I'm going to do is I'm going to start a fuzzing job on the master. It's going to generate some fuzzing tasks for each of the targets. And once it's done that, it'll start powering up each of these targets one by one. So if you watch the lights on the relay, and if you listen carefully, you can hear the relays clicking. You'll see that each of these targets is powering up one by one. If you watch the little green LEDs on the targets, you'll see them coming up. And it'll take about 2 minutes for those targets to completely come up. But once it does, we can actually start to see some fuzzing results occurring. So what we're seeing scrolling by on the master system now is every once in a while you'll see a state diff. There was one, scroll by on the screen. And the master is recording each of those diffs as they occur. And my hope is that I'll be able to analyze those diffs offline later in order to detect what changes each instruction is having. But of course, every once in a while, one of these instructions will lock the system. And you can see the relay blinking as the master is now resetting frozen target systems. So this thing ran for about 3 weeks. I collected 15 gigabytes of logs, about 2.3 million different state diffs for 4,000 hours of compute time in order to try to gather enough information to reverse engineer this unknown instruction set. So the very first thing I wanted to figure out after I collected this giant collection of logs was, is any of my theory correct? Am I actually able to circumvent ring protections through this embedded RISC core on the processor? And I was really excited when I found this first instruction, A7719563, an instruction that I executed in ring 3, sending that instruction over to the deeply embedded core from the bridge instruction. And we can see that EDX got loaded with a new value here. EDX became 800500033. That is the value of the control register 0. So CR0 is supposed to be a register that is only accessible to ring 0, but we just read it in ring 3 using the deeply embedded core. And we're not just limited to leaking data from ring 0. We can actually write data that only ring 0 should have access to. So for example, only ring 0 should be able to modify the debug registers in x86, but here we can actually see that this DEC instruction, this deeply embedded instruction, was able to write the value of EBP into the DR0 register. So this is a really good sign. Things were looking promising to be able to use this backdoor for privilege escalation purposes. So really, when we've started tearing down the boundaries of rings, when we can reach directly into the kernel, we can do whatever we want at that point. But I wanted to come up with some sort of simple, interesting proof of concept payload to demonstrate the capabilities of this deeply embedded core on the processor. So I thought an easy proof of concept would be privilege escalation payload. And the privilege escalation payload would look something like this. So the very first thing we want to do is we want to read the global descriptor table register in x86. The global descriptor table register is going to point us to the global descriptor table, and one of the entries in the global descriptor table is going to be for the FS segment register. We can, theoretically, if we can circumvent ring protections, we can reach directly into kernel memory and pull out that segment descriptor from the global descriptor table. And there's some bit fields in that segment descriptor that will give us a pointer to our process's task structure. And again, if we are able to reach into kernel memory and pull out information, we can grab a pointer to what's called the CRED structure that sits within this task structure. So the CRED structure is going to hold my process's permissions. So with access to the credential structure, what I'm going to do is I'm going to give myself root permissions. Root in Linux is basically defined by 0. So I'm going to use my ring circumvention techniques in order to write the value root to the UID, the GID, the EUID, and the EGID in that credentials structure. So at least that's what our payload theoretically looks like. The next question is, can we actually build this thing using this deeply embedded core? Now, if you look carefully at the payload, there's really only a few places where we actually bypass the ring boundaries, where we actually reach into ring 0 and start modifying things. So those are really the only places where I need this deeply embedded core to do my work for me. But it is kind of fun to write instructions for this secret core on the processor and make it do interesting things. So I thought it'd be a little more interesting to actually try to write this entire payload in instructions for that deeply embedded core, as opposed to just the kernel accesses that I needed. So to build that payload, well, I'm in a situation where I've got 15 gigabytes of logs. I've basically got to start sifting through this thing for primitives. So this actually starts to feel a lot like building a ROP chain, where conceptually I know what I'm trying to accomplish, but I need to figure out how to use my individual pieces in order to accomplish that. So we can start looking through those logs for some things to help us out. So for example, I want to find a GDT read instruction from that DEC core. And sure enough, I can find A313, which seems to read the global descriptor table register into the EBX register. I need a kernel read primitive. I need some way to read kernel memory from that deeply embedded core. And sure enough, I can find an instruction that does that. D407 read this single byte out of kernel memory and into a processor register. I need a kernel write privilege. I can find that too. E2B7 does exactly that. It wrote the low bit of ECX into a kernel memory buffer. So this is promising, but sifting through these logs like this just doesn't scale very well. I really wanted to be able to write robust payloads, a lot of different things for this deeply embedded core. So I needed some way to automate this approach that wouldn't require me to manually go through 15 gigabytes of logs. So I started looking for a way to reverse engineer this deeply embedded instruction set in an automated fashion. So my idea here was if we could extract instruction behavior from this set of state diffs, I could start to identify bit patterns in these RISC instructions. So I built a tool for this that I called the collector. And basically what that's going to do is it's going to help us automatically reverse engineer this unknown instruction set. So the collector starts out by trying to look at state diffs and identify basic patterns in them. So for example, it'll look for words being copied around in a state diff. It'll look for immediate values being loaded into registers. It'll look for one register being transferred to another register. It'll look for memory writes, memory reads, increments, decrements, shifts, immediate loads. It'll look for various arithmetic and bitwise instructions just by looking at patterns in these state differential records. So what it will give you is it will start classifying instructions based on the patterns that it observed. So for example, here, it's telling me, well, these are all the instructions that I found for you that transferred information from one register to another. Now, the very first thing the collector is going to do at this point, after it generates this instruction bin, is it's going to try to resolve what do these individual bits mean in this instruction. So through some manual analysis, I was able to figure out, for example, that the EAX register is encoded by the bits 0000, and the ECX register is encoded by the bits 0001. So the first thing the collector is going to do is it's going to check for each of these instructions based on the register change that I'm observing. Can I find those bit patterns somewhere in this instruction? So it'll pull out patterns like this. This is basically everywhere in this entire set of data that those individual registers could have been encoded in their corresponding instructions. And what you'll see is that there are patterns here. There's only one location in this set of this set of instructions where that pattern is consistent. So the collector is able to infer, well, it has to be these two columns encoding your registers, one column encoding the source, one column encoding the destination. And we can use that same technique to pull out other bit patterns. So for example, here we're trying to resolve what opcodes are being used to encode these different instructions. And you'll see that it's not perfect. Ideally, we would see all these registers or all these instructions with exactly the same opcode pattern. That's not what we see. Some of the later ones don't really follow the patterns that we saw on some of the earlier ones, but that's okay. The collector will deal with that. It'll just try to pick out the patterns that are the most probable or the most common. It'll even do things like try to pick out don't care bits or bits that have some unusual statistical properties that might indicate that they do something even though we don't know what they did. And then it'll jam all this information together in order to automatically derive a bit encoding for that specific instruction. So based on the bins that the collector was finding, these are sort of the encodings that it came up with and the basic instructions I had to work with for the deeply embedded core. I've got instructions to load the global descriptor table. I've got instructions to move data around, load immediate values, read data out of memory, write data to memory. I've got all the basic primitives I need now in order to implement that payload that I was trying to implement. So at this point, I decided to go all out and I wrote a complete assembler for this custom assembly language that I called the DICE assembler, which basically means that I can write instructions in one of their primitive forms like this at a high level and then get it encoded into a binary format. I can then wrap each of those instructions in the x86 bridge instruction and send that instruction over to the RISC core in order to execute that instruction. So looking at our payload again in DICE assembly, it looks something like this. We grab the global descriptor table register. We calculate an offset to that FS descriptor. We use our ring circumvention instructions in order to pull that descriptor directly out of kernel memory and parse its bit patterns. At that point, we've got a pointer to the task struct. So we'll pull apart that pointer in order to get a pointer to the cred struct. We'll pull apart that pointer in order to start writing out the UID, the GID, the EUID, and the EGID fields, all in this custom deeply embedded instruction set for that alternate core on the processor. So collectively, that looks something like this when we actually build that into a working payload. We've got our introductory instructions that are going to be the launch instruction to activate the deeply embedded core. And then we've got each of those assembled DICE instructions wrapped in the bridge instructions so that I can feed it over to that embedded core. Finally, when we're done, we launch a shell in order to try to get our privilege escalation. So one more time, revisiting that demo from the beginning, now that we understand how all the different pieces work. We began by unlocking the back door by executing that secret x86 launch instruction that was enabled by the God mode bit. After we've executed the launch instruction, the processor is ready to start accepting RISC instructions, but we're only able to get those instructions over to the RISC core by wrapping the instruction in the x86 bridge instruction. So that bound EAX instruction is now how we can send these individual RISC instructions over to that deeply embedded core in order to get it to execute exactly what we want, in order to make it circumvent the processor security checks that we're trying to get around. Finally, we'll execute a shell in order to view our results. So once again, we simply compile this program and check who we are. We're still a regular user. We'll relaunch this program and see that we've become root. So I'm only going to half seriously throw this out, but this is sort of like a ring -4 on the processor. So ring -3 was a core that was completely separate from the x86 processor. This is a little bit more deeply embedded. It's sort of a secret co-located core alongside the x86 core. Unlike ring -3, it has unrestricted access to the x86 core's register filed. It's got shared execution pipeline with the x86 core, which in many ways makes this more powerful than ring -3 was, but at the same time, the whole thing's nebulous this deep, and the whole ring model has sort of completely shattered by this point, but it is sort of an interesting thing to think about. So that leaves us with this. This is direct ring 3 to ring 0 hardware privilege escalation on x86. This has never been done. Every other attempt at this kind of thing has used operating system code or other program code in order to exploit some flaw. This is purely a hardware circumvention mechanism for the fundamental ring privilege model behind all of our processors. Fortunately, it shouldn't be that big of a deal. We still need ring 0 access in order to get this whole thing kicked off. The whole rest of the pipeline can be done in ring 3, but the first change that toggling the God mode bit had to be done with ring 0 access. At least that's the theory. As I started poking around some of these other systems I had in my stockpile, that turned out to not be the case. So what we're looking at here is another VSC3 processor. This is a Samuel 2 core. I've just booted up this system from scratch. Nothing else has been modified. Nothing else has been touched on it. And we're going to log in as a normal unprivileged user. I could have dumped all this over serial. I didn't have the right setup for that. But after we log into the system, and what we're going to do is install the MSR kernel module in order to gain access to the MSR bits. We're not going to modify them, but I am going to read them out. I don't have the read MSR tool on this, so I'm just going to hex dump out those specific MSR bits. So I'm looking at the global configuration register on this processor. And when I do that, you'll see the low byte of the global configuration register is D7. That is 11010111. The low bit of this register is the God mode bit. That means the God mode bit is active by default on a freshly booted Samuel 2 core. That means that any unprivileged code on this system could have accessed the kernel at any time, which is a scary prospect. And when you sort of blow away the x86 ring protection model entirely, all of our other protections fall apart. Antivirus does nothing now. ASLR, DEP, they're easily circumvented when you can just directly reach into ring 0. Code signing, control flow integrity, kernel integrity checks don't do anything when there's no more separation between the rings. So it's a scary prospect, but there are mitigations. So one approach would be to update the microcode to lock down the God mode bit, or we could update microcode to disable the bridge instructions so that we couldn't feed instructions to the deeply embedded core. Alternatively, we could update the OS and firmware to disable that God mode bit and just periodically check its status to make sure it hasn't been enabled. But at the end of the day, this is an old processor. It's not in widespread use, and I don't mean to throw VIA under the bus. I think this was a good idea that just had a flaw in its implementation. Their target market was embedded, and this was probably a useful feature for their customers. So instead, we should take this as a case study. Backdoors do exist in hardware, but we can find them with the right techniques. So looking forward, I do think this is a big deal. This isn't just a C3 problem. This isn't just an x86 problem. This is an overall flaw or an overall problem in all of computer engineering, where these black boxes that we're trusting for all of our computation, we have no way to introspect them. So whether or not these hardware backdoors exist anywhere else, this is a problem that's going to continue to haunt us until we have a way to look into these black boxes. So I think that's the big takeaway here is whenever we find something secretive or off limits, we as security researchers need to push deeper because that's how we establish trust. That's how cybersecurity should work. So along those lines, I've open sourced all this information. All the tools, techniques, code, and data from this are available online now. You can scan anything, scan everything, and I really, really hope people will build off of this for future research in order to dive deeper and deeper into processor security. I do want to quickly pitch a side project, Project Night Shift. I'll talk more about this in a few days, but it turns out that you can use that side channel attack that I demonstrated in order to reveal password protected registers in some x86 processors. So I'll be demonstrating that at DEF CON if you're around. But beyond that, you can find all this work right now on my GitHub. That's github.com, XOR EAX, EAX, EAX. That's Project Rosenbridge is this specific project. You can also find the Sand Sifter fuzzer there, the Mobfuscator single instruction C compilers there, some other fun stuff I've done over the years is all there. If you have any feedback or ideas on this, I would absolutely love to hear it. I'm not totally out of time now, but you can grab me after the talk. You can shoot me an email or contact me on Twitter at XOR EAX, 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 or same thing at gmail.com. So thank you everybody for attending, and that's all I've got.